Hey, everybody. I know I have a video or a couple of videos that introduce the ideas behind infinite sequences and infinite series. But in this video, what I wanted to do is try to connect these things conceptually to some of the other kinds of objects in our class that we're maybe more familiar with, specifically functions and improper integrals. So we've already been looking at functions for probably years and years and years, right? We start looking at functions way, way back in our math education history, but only very recently have we talked about improper integrals. So what I want to do is try and make a connection between sequences, which maybe we've seen some stuff about before, but likely not, and infinite series, which likely we really haven't seen much about at all. So let's do that. First, we have this thing called a sequence of terms. We really just list this out. A sub n, n is a little subscript. We really might just write this as A1, A2, up to AN, and then forever and ever and ever after that. We have these little index things on here where we can kind of count from n equals 1 up to infinity. And the main thing here is that this is just a list of terms that we can say the first term, a sub 1, the second term, a sub 2, the third term, a sub 3, etc., etc., etc. And we maybe have some kind of formulaic way of building these terms, but maybe it's just something that we describe. Doesn't really matter. As long as we have some way of getting this infinite number of numbers, we can just write them in a list in order. We put these little curly braces around them because this is kind of like a set, but I'm not going to worry too much about the notation or anything like that here. And then here with our infinite series, we just have that this is all of these terms added up. Well, what we find out is that this is really hard for us to do up to, a sub n, et cetera, et cetera, et cetera. Well, first I'll notice we changed the letter here. I don't really know why this is the case, but in a lot of introductory calculus textbooks, we use different subscript letters for sequences and series. I'm not really sure why, to be completely honest. You see a mix of N's and K's normally in here, and that's because those are continually used for like the natural numbers or like positive integers or things like that. Just like X is normally used as an input variable and F is normally used as our name for a function, A is normally used as the name of a sequence, and N or K are used as the index normally. But anyways, we find that it's hard to add these things up. And so we have this idea of a partial sum, right? And we take a look at a partial sum, but I want to investigate that in just a minute. So what I'm going to do is I'm going to kind of block this off, and we're going to think about how we've been analyzing functions so far and how we've been dealing with those things. We have some function. Oops, my straight line tool is on. We have some function called f of x, and we can take a look at what that function might be. It's going to be something that we have a formula for. And what we can do is we can get pairs, right? X inputs and Y outputs. And then we can plot all these points on a graph. So maybe we have some graph that looks like this. Or something like that. What we'll notice then is that these are kind of like a sequence in that there are inputs and outputs, but it's a little bit different. With a sequence, we're limited to only taking in positive integer inputs. 1, 2, 3, 4, up to whatever, n, and so on and so forth. Whereas with functions, we can put any real number into these normally. Maybe we have some, limitations in our domain. For instance, the function 1 over x, we might say that 0 is not in the domain because we don't want to deal with 1 over 0. We don't want to divide by 0. Square root functions and logs and all these other functions might have some restrictions in the kinds of values that you can put in. But in general, we might think about just subsets of real numbers. take some real numbers, maybe they're integers, but maybe not, and plug them in. For a lot of functions, we might care about what's going on at the x value of a half or a third, or maybe something irrational like square root 2 or something like that. With sequences, we don't get that flexibility. We're just limited to a domain of positive integers here. Other than that, these things are going to act really similarly. Now, if an infinite series is what happens when you add up all of the sequence terms, then we can try and think about what it is when we add up all of the values in a function. And what this is an integral. And so we can compare that infinite series to this improper integral from 1 to infinity, maybe, of f of x dx. And then we can say, well, we really don't do that, right? What we've learned is that the way that we might attack this or deal with this is by using a limit as, I'm going to use t because that's what I like to use. As t goes to infinity from 1 up to t of f of x dx. And then we'll go ahead and integrate this way. The reason we do this, remember, is that we can say, well, if t is a real number, then we can go ahead and use the fundamental theorem of calculus on this as long as our function is integrable. If we can find an antiderivative, then we can go from there. And we're going to have some expression in terms of t at the end. Well, we can then just apply a limit as t goes to infinity, and we can see if this integral converges, if that limit exists, or if it diverges. Maybe the limit goes off to infinity or negative infinity, or maybe it just doesn't exist in some other way. We're going to use a similar approach for dealing with an infinite series. Instead of thinking about adding up all of these infinite number of things, what we might do is look at a limit as n goes to infinity of this series. What you're going to notice is we're doing the same trick, right? We're just swapping out infinity for a variable, and we're doing the exact same thing right here. We're going to swap out infinity for a variable and look at a limit. That way we can assume that this is actually some finite sum. We call it a partial sum because it's a part of an infinite sum. And we'll say, well, let's just add up the first bunch of terms, and then we're just going to keep making this n value get bigger and bigger and bigger and see if we can find some expression in terms of n. Just like over here, we might integrate this thing and find some value expression in terms of t and apply a limit. Well, we're going to do the same thing. If we can figure out what this sum goes to in terms of n, then we can apply this limit as n goes to infinity and deal with our infinite series. So that's how we can connect this idea of sequences and series to functions and integrals. It's really the same kinds of thing. We're just restricting the domain of the functions. And what you're going to notice is that then that's going to kind of change how we think about, dx and all that kind of stuff. If dx is this spacing between x values that gets infinitely tiny here, then you can think, well, the spacing in between our sequence of terms doesn't really change. We can't really do that. Because these are on a restricted domain of just positive integers, all the spacing is just like 1, right? And so you can think it really has the same kind of structure and the same kind of interpretation, other than the fact that we're restricting our kinds of functions to just taking in only positive integer inputs instead of, real numbers or some subset of the real numbers. Okay, so let's take a look at an example. What I want to do is I want to think about this function here. Let's consider this function 9 over 10 to the x, or 9 10 to the negative x. You might remember that exponential functions always kind of look the same. Exponential functions normally look like this. This would be like 10 to the x. And then we just are going to be scaling them based on what the base is. So maybe I'll say b to the x for some base. Since we have a negative x, though, that's going to be flipping this thing horizontally. And then we have a bunch of like scaling going on. The base of 10 is really going to change vertically where this thing goes when x is 0. And then we're going to multiply by 9. And again, that's going to be scaling stuff. But really, this function is going to look like this. We're going to have some sort of a horizontal asymptote. When x is 0, then what we're going to have is that this is at 9. And I apologize, I misspoke. I said that the 10 scales things for when x is 0. That's a lie. When x is 0, every exponential is 1. It scales things for when x is 1. And then this coefficient scales things when x is 0. So this is at a y value of 9, right? So maybe I'll say 0, 9. And then we have like a point right here with an x value of 1, where now this is where our base is going to come into play. And now we've got this 9/10. And so there's our exponential function. What we're going to notice is that if we think about the integral from 1 to infinity, we're going to be thinking about this kind of shaded in area. Now, what you're going to notice is that this horizontal asymptote is super important, because if this horizontal asymptote wasn't there, then we could pretty much just say, like, I know that this integral is going to diverge, because that means that we're never going to get to this spot where we are adding a tiny, tiny amount of area where maybe the extra area that we're adding is so small that it doesn't make a difference, and then we have this nice limit, right? If we had a horizontal asymptote that was above, maybe at like y = 1, then we're just going to continually have all this area trapped between our function and the x-axis. But since our function is diving towards the x-axis with this horizontal asymptote, we have a hope of this integral actually converging to something. Now, that doesn't guarantee that it will. Maybe our function doesn't go to our x-axis fast enough, right? And we had this kind of weird kind of idea of what that really means. But really, we can just try and investigate what happens with the limit. So let's go ahead and do that. We know that what this really is a limit, or maybe the way that we're going to think about it, I'll say, a limit as t goes to infinity of the integral from 1 to t of 9 times 10 to the negative x dx. And maybe I'll pause it here, or I'll let you pause it and see if you can work this out. You might have to remember the integral rule for exponentials. We probably haven't used it since Calc 1, and so that's something that we'll have to think about. But not a big deal. Look that up. If you don't want to, I'm going to do it in a second, so feel free to just watch. You finished? All right, I'm going to keep going. If you want, pause it, and you can do it. So let's just take a look at the derivative of an exponential function, and then we'll find the antiderivative, and then we'll think about how that negative x plays into here. So the derivative of an exponential function, like 10 to the x, is going to be 10 to the x natural log of the base. We multiply by the natural log of the base. You can go and look at a Calc 1 video that I've got up here to show you why that is the case, but whatever. That means that we have this extra coefficient that if we're going backwards, we actually don't want here. And so what we're going to do is say the antiderivative of 10 to the x is actually going to be 10 to the x divided by the natural log of the base. Right now, plus c. Now, if we differentiate this, we're going to have the natural log of 10 in the denominator. We're really just dividing by natural log of 10 everywhere, right? So that works itself out pretty nicely. So here's our antiderivative, but then we also have this negative x in here. You can do a tiny u substitution to see how this goes, but what we're really going to notice is that that's just going to go ahead and kind of float its way out with an extra negative sign from the chain rule, right? So let's go ahead and do this. Our antiderivative of 9, 10 to the negative x is going to be negative 9 times 10 to the negative x over natural log of 10. Now we still need a limit on here. And then we're going to evaluate this from x equals 1 up to x equals t. Cool. This 10 to the negative x I can really put in my denominator. So this is actually a limit as t goes to infinity of negative 9 over 10 to the x natural log 10 evaluated from x equals 1 up to x equals t. We're pretty much going to see what happens when t gets in here and goes off to infinity. But let's go ahead and write it all out. So this is a limit as t goes to infinity of negative 9 over 10 to the t natural log 10 minus negative 9 over 10 to the 1 natural log 10. Cool. What you're going to notice is that when t goes off to infinity, this part here is going to go to infinity. And that means we're going to be dividing by infinity. And so that means this whole thing is going to go to 0. So we are left with positive 9 over 10 natural log 10. And that's what this shaded in area converges to. So again, we're not doing anything groundbreaking here. This is the same kind of stuff that we did when we were learning about improper integrals. It's maybe a different type of function than we looked at, right? So we maybe have to brush off our antiderivative rules for exponentials. But outside of that, there's really not much new going on here. We're going to look at this kind of partial integral where we use this replacement proxy variable of t, that is going to be some real number, and then we're going to look at what happens as t goes off to infinity in our fundamental theorem of calculus answer that we get. Cool. All right, let's do the same thing, but let's think about the sequence version of this. So now instead of thinking about our function, what we're going to do is just kind of figure out what this sequence looks like. Now, this is a sequence from n equals 1 to infinity, which means that we don't have this point over here when our input is 0. Our first point is right here when n is equal to 1. So we have this point right here, right? When n is equal to 1, we get, maybe I'll do this, that a sub 1 is 9 over 10. Or if you want, you can think about it this as 0.9. When n is equal to 2, we get that a sub 2 is 9 over 100, or you could think about this as 0.09. So we could go ahead and plot that point. And when n is equal to 3, we get a sub 3, which is 9 over 10 cubed, which is 1,000, or we get 0.009. And you can kind of see the formula, the pattern here, right? At some point, this is going to be very difficult for me to draw accurately because all these points are going to be so close to this asymptote. But notice I'm not drawing a line here. I'm just plotting points because there's nothing in between these points. The domain of our function, you can think, is just the set of positive integers from n equals 1 up to infinity. So there is no point at half or a third or anything like that. And so we really don't draw a line connecting these because those lines that we draw up here, this curve, really represents an infinite number of points that we're passing through. And here, we still have an infinite number of points, but we don't have all the points in between here. So that's something. Okay, notice we still have this kind of asymptote. And so we still have the fact that these points are going to approach 0, which is going to be helpful and good later on. But for now, let's go ahead and think about this sum. What we want to do is we want to write this as the limit as n goes to infinity of the sum from k equals 1 up to n of 9 over 10 to the k. We call this the partial sum. S sub n, a sum up to the nth term. And so what we're going to do here is we're going to see if we can find what these partial sums look like. And if we can find what these partial sums look like, then maybe we can come up with what this limit is actually going to be, and then we can see what's going on. So let's go ahead and do that with these partial sums. S sub 1 is the sum from k equals 1 up to 1 of 9 over 10 to the k. That is just 9 over 10, or if you want, 0.9. But S sub 2 is going to be a sum from k equals 1 up to 2 of 9 over 10 to the k. And that's 9 over 10 plus 9 over 100, or 0.9 plus 0.09, 0.99. S sub 3 is going to be the first 3 terms. So what we're really doing is we're taking these terms that we found individually and we're just adding them up cumulatively, right? So for the first partial sum, we just look at the first term. For the second partial sum, we look at the first 2 terms added up. For the third partial sum, we look at the first 3 terms added up, etc., etc., etc. And so here we've got 9 over 10 plus 9 over 100 plus 9 over 1,000, or if you want, you can write this as decimals, 0.9 plus 0.09 plus 0.009, which is 0.999. And you can see how this is going to go, right? The fourth partial sum is going to be the third partial sum plus the fourth term. So it's going to be this 0.999 plus 0.0009. So we can write out more of these. And we could keep going. What we might care about, though, is this pink one, S sub n, because what we really want is the limit as n goes to infinity of S sub n. So let's try and think about what this looks like. Now, at this point, let's just play the pattern recognition game. Let's not dive into any formulas that we have or might learn about in the future or anything like that. Let's just think about what's going on with these terms. Can you explain the pattern? 0.9, 0.99, 0.999, 0.9999, 0.99999. Oh, it's getting hard to count these things. S sub n is going to be 0.9999999 n times, right? It's 5 n's or 5 nines and 4 nines and 3 nines after the decimal. That's a hard thing to just write out, though. And so we'd like to come up with some sort of expression for this. Now, there are some formulas to do this, but I think it's easy enough to just sit and think about this. Maybe not easy, but it's accessible enough for us to just sit and think about this and come up with a formula. What you're going to notice is that these things are really like, well, maybe I'll write them out this way. So then we'll get S sub n. This was 0.9. This was 0.99. This is 3 nines, 4 nines, 5 nines. Ooh, that's getting hard to write. What we might notice is that that's really 1 minus 0.1. And this is 1 minus 0.01. And this is 1 minus 0.001. And this is 1 minus 0.0001. Did I get that right? Yeah. And then this is 1 minus 0.00001. I say that this is easier for us to get a formula for because these are just 1 over powers of 10. This is 1 over 10. This is 1 over 100, 1 over 1,000, 1 over 10,000, etc., etc., etc. So S sub n is 1 minus 1 over 10 to the n. So again, S sub 1 is 1 over 10, or 1 minus 1 over 10, sorry. S sub 2 is 1 over 1 minus 100. S sub 3, etc., etc., etc. Now remember, these aren't terms of the sequence. These are partial sums. But what we care about is the limit of these partial sums. So let's take a look. The way that we've written this out conveniently is actually quite easy to deal with this limit. Since this is our partial sum, which is us saying the same thing as getting an expression for this antiderivative evaluated, we're going to look at a limit as n goes to infinity, which is the same thing as looking at the limit as t went to infinity in the improper integral. And we're going to get a value for this. Pretty quickly, what you're going to notice is that this part here is going to go to infinity in the denominator, meaning this whole fraction is going to go to 0. So this limit is 1 minus 0, which is 1. Cool. It's a different value than what we got for our integral, which maybe makes sense. Our integral was all this area shaded in under a curve here. And what we're looking at now is just adding the heights of all of these points together. So it's a little bit different, right? But it's pretty similar. Okay, what did we just do in reality? Because this is actually one of my favorite problems to show calc students. Here's what we just did. You ready for this? We just showed that the repeating decimal, 0.999999999 forever, is equal to 1. What? How are those the same number? What we just showed is that if this ... really does mean keep tacking on 9s at the end of this decimal forever and ever and ever, then we set up an expression to do that. This infinite sum is exactly that. It is exactly a way for us to formalize tacking on 9s at the end of our decimal forever and ever and ever. We keep adding an extra 0.0009 or 0.000009 or whatever. We've got these partial sums that say just take a tiny, tiny, tiny bit away from 1. Keep taking a smaller amount away from 1. And as we do that forever and ever and ever, just a tiny, 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 tiny bit away from 1, eventually we're really not taking anything away from 1. And so it's 1. This ... here represents a limiting type of operation, we'll say. And so 0.9999999 is 1. There are lots of ways that we can do some strange things like this that maybe can break our intuition. But hopefully this example gives you a bit of an idea of how to connect sequences and series to some objects or things like functions and integrals that we have a bit more comfortability and familiarity with. As we move forward, we are not going to do this partial sum method that we did here, where we try and find an explicit formula for the partial sum, because what we're going to find is that in general, this pattern recognition thing is very difficult. Overall, that's a very, very hard thing to do. And so in general, it's going to be really hard for us to tell what a series converges to, because it's going to be hard for us to get this formula for the partial sum that we can apply a limit to. But we can use this concept to be able to analyze series to figure out if they do actually converge, add up to a real number or not. And in some cases, we will be able to figure out what specifically they converge to, but it's going to take a little bit of work for us. Cool? Hopefully that's helpful. We will go over more of this stuff in class when we get back. Awesome.